Let's now take a look at this problem. Suppose that b and d are relatively prime. Suppose that a and b are relatively prime, and suppose that c and d are relatively prime. Prove that ad plus bc over b times d is in simplest form. Before we get started on this, I want to note that ad over bd, that of course is a over b. And if I look at the second term, bc over bd, that is equal to c over d. So we're assuming that the fraction a over b is in lowest terms. A and b are relatively prime. C and d are relatively prime, so the second fraction is in lowest terms. And also there are no common factors of the two denominators, b and d. So if that happens, we want to prove that when I add the fractions together, it is already in simplest form and there's going to be no common factors to cancel out. The way that we're going to do this is as follows. So let P be a prime factor of the denominator b times d. So suppose I have a prime factor of the denominator. I will show that p is not a factor of the numerator. So if this happens, if any prime factor of the denominator is not a factor of the numerator, that means that the only possibility is that the only possible prime factor of both, the only possible factor of the numerator and the denominator is 1, because no prime factor can go into both the numerator and the denominator. And this will prove that it's in simplest form. Okay, so let b divide b times d. Then from a theorem that we proved in class, then p divides b, or p divides d. If a prime divides a product, then the prime must divide one of the two factors. Okay, so let's take this one at a time. Case 1. P divides b implies, if p divides b, then that means that p must divide the second term of the numerator, b times c. Also, if p divides b, that implies that p does not divide a. And the reason is because the greatest common divisor of a and b is equal to 1. So if p is a prime factor of b, then p cannot be a factor of a, because the only common factor of a and b is 1, and if p is prime, p must be greater than 1. Also, p cannot divide d, pardon me. The reason is because b and d are relatively prime, and so if p divides b, then p cannot divide d. So if p does not divide a and p does not divide d, that means that p does not divide a times d. This is a theorem we proved in class. It's actually the contrapositive of the theorem we just used a second ago. We just said if p divides a product, then p divides b, or p divides d. Going the other direction, if p does not divide a and p does not divide d, that implies that p does not divide the product a times d. So that's the contrapositive of the thing that we just used. Okay, so p divides b times c, p does not divide a times d, and therefore you should convince yourself that that implies that, so these two statements implies that p does not divide a times d plus b times c. B times c is a multiple of p. A times d is not a multiple of p, so I cannot factor a p out of the right-hand side. And so p does not divide a times d plus b times c. Okay, so that's case 1 if p divides b. Let's now proceed with case 2. And you might want to stop the video at this point and see if you can do that on your own. The logic will be very similar. And then restart. Okay, let's now do case 2. Case 2 is that P divides D. P divides B or P divides D, so let's try this as case 2. If P divides D, then clearly P divides the first term in the numerator, A times D. Also, P divides D implies that, well, C and D are relatively prime, so if P is a factor of D, that means that P cannot be a factor of C. Also, if P divides D, B and D are relatively prime, so that means P does not divide P. And so if P does not divide C and P does not divide B, that implies that P does not divide B times C. So P does not divide A times D plus B times C. So either way, P does not divide the numerator. So the greatest common divisor of B times D and the numerator of AD plus BC must be equal to 1. Because there can be no prime factor of both the numerator and the denominator. And that proves that this fraction is in simplest terms, and that is the end of the proof.